Hello, and welcome to another edition of Math, Music, and More. Today's going to be a speed round because I'm actually supposed to be in the gym over there, but this thing that I recorded yesterday regarding countable infinity was bothering me so much, I just can't get it off of my mind until I finally resolve it. So point number one, hope you loved the video where I was talking about rational numbers in the final portion of my video on countable infinity and how you could construct this sort of pyramid to demonstrate that even something as rich and dense as rational numbers are countably infinite. But one thing that you may have all realized is that this thing doesn't have any negative components to it. So how do we do this so that we actually can include negative numbers as well? And the simple answer that I have to that is we just create another triangle or pyramid, whatever you want to call it, over here that exactly mirrors it, but it has negative values everywhere. You just do this exact same thing, but with negative values. And then all you have to do to demonstrate that this is still a countably infinite set is just you bounce back and forth between the triangles as your choice function, as far as your protocol or your algorithm, as you go from n equals 1 to n equals 2 off to infinity, again, to create that mapping between the sets. So you could start here with 0, then you go to 1, then you go to a half, then you jump to negative half, then you jump here for a third, then negative a third, and you just keep bouncing back and forth. That way you have actually proven that there is a bijective mapping from the natural numbers to the set of both positive and negative rational numbers. So there, proven. And what's also very fascinating about this little side exercise that we just did right now is that you realize that doing this on its own would already be countably infinite. And yet doing this in the negative number space is also countably infinite. Well, what does that imply? It means that countable infinity plus countable infinity is still only countably infinite, the smallest of infinities. However, many of you are saying, hey, great job, but come on. You're trying to pull one over on us because everything that you did here was just within the line segment of 0 to 1. And everything you did here in this mirror image was just between 0 and negative 1. Come on, we want to know this thing for the entire space of rational numbers. So here's my trick that I just came up with this morning. I'm going to create rays on both triangles, and I will only demonstrate it in this one here. But you basically create rays coming off of every single reduced form of 1. It could be 2 over 2. It could be 3 over 3, it could be 4 over 4, and not only could be, it will be, and you do it ad infinitum all the way down this boundary of the triangle. And what do you include? Instead of within the triangle, where we're always adding 1 to the denominator, in this case, in these rays emanating from the boundary, we add 1 to the numerator. So this would be 3 over 2, and then it jumps to 4 over 2. And here, for example, we would have 6 over 4 that jumps to 8 over 4. And then you have everything in between, right? Like 7 over 4 and 5 over 4. And here, of course, you have a 4 over 3 and 5 over 3 and 6 over 3. Sorry that it's so sloppy. And then you notice, just as in this pyramid or triangle, we had to get rid of repeating terms by always wiping out the values underneath. And every time you have a first entry in the pyramid, you just wipe out everything underneath. Here we would do something very similar. Every time you have a value for the first time on the uppermost ray, you knock out everything underneath it, right? And you just keep going. Here you have 3.5, you wipe out everything underneath it. So great, geometrically that makes sense, but we still need some sort of protocol to ensure that we can demonstrate that we have a bijective mapping between natural numbers and this crazy thing of dual pyramids and dual rays, because this one will also have rays in order to capture the negative side and going outside of that interval of 0 to negative 1. So how do we do that? This is what I suggest. The protocol is simply, you start here, you go to 1, you go to negative 1, you come back, you go to a half, you go to negative a half. Then since you're on this row of the triangle or the pyramid of a half, you go to the first ray and you go out just 1. You bounce back to this one and you go out just 1. Once you're done with that, you go back here, you attack the next row and you go out just 1. You go back to this one, you do the whole row, you go out just 1. Then you come back and you go out, you pop back up to the second ray, do the next one, pop down, do the next one, Same thing here. Do the next one on ray -2, ray -3, and then do the next row. 1, 2, 3, go out 1. And then you start the whole process again. 1, 2, 3, 4, go out 1. And after every sequential move, you always pop back up to the ray 2/2, or that emanates from 2/2, and then the one that emanates from -2/2, and then to the thirds, and then to the fourths. In this way, you're always hopping back and forth between both pyramids and all rays. And this way, you can, vehemently conclude that this is in fact a bijective mapping between the natural numbers and everything we created. Why am I spending all this time on this weird protocol? Picture if we wouldn't have created this protocol. Picture if we would say, well, we start by counting all these. Well, you're so busy counting all these to infinity, in fact, that you never get to touch this triangle, so to speak, and you never get to touch any of those rays. And that's not a proof at all, because you're not actually addressing those values of the rational number space. And this is exactly why I not only created this geometric visual representation, but at the same time thought about how do you set up the right algorithm to bounce back and forth to make sure you are always hitting every single rational number. My final comment is, just as when we created the parallel mirror image of the negative space, we were thereby able to prove that countable infinity plus countable infinity equals yet another countable infinity. Fascinating. But keep in mind that by doing the rays, what did we do? We took a proof of just 0 to 1, and if you add the negative triangle, 0 to -1, and we showed that it also holds for the intervals 1 to 2, 2 to 3, 3 to 4, 4 to 5, and so on and so on. Well, how many different line segments are there? There are a countably infinite number of line segments. What I'm implying here, I hope you get it, is that this addition of the rays not only proves that the rational numbers are countably infinite, but it actually proves also that countable infinity times countable infinity is still countable infinity. So I'll leave it at that, and I'll just leave you with a little bit of cliffhanger. My God, if you can add countable infinity to countable infinity, hey, you can even do it 1,000 times, it's still countably infinite. And wow, if you even take countable infinity and multiply it by countable infinity, you still have countable infinity. How could you possibly have something bigger than that? What is this thing that you're leading us to called uncountable infinity? And how in all of God's graciousness could there be an infinite variety of sizes of uncountable infinity? That's my cliffhanger. Hope you liked it. This was eating me up, so I had to resolve it. Like, subscribe, comment. Very much look forward to your reaction to this video. Have a great day, everybody. Time to work out.